stream hydrograph analysis are useful for estimating some of the basic fluxes in the watershed. In particular, for groundwater models, stream hydrograph analysis can be used to estimate recharge, at least an average recharge over a watershed. It can also be used to estimate how that recharge varies with time, which can be a useful thing. So what we'll do is separate the base flow and storm flow, separate the hydrograph into those two components, identify what's called a base flow recession, where recharge is assumed to be essentially zero, and then also identify periods of recharge where the aquifer is being replenished, and then analyze this to estimate the fluxes. So this is a useful technique because the data on flow in streams is fairly readily available in the U.S. The USGS operates a network of stream gauges, and they are located here, at least some of them. And at these locations, you can get records of the daily flow in the stream for up to many decades, so a fairly long-term record. South Carolina has a variety of gauging stations, and you can see them located here. Altogether, there are about 25,000 sites in the U.S. that have records. About less than half of them are active today, but some of them, the other half, have historical records. Okay, so here's the basic idea. If you look at the flow in the stream and you plot it up as a function of time, that's a stream hydrograph. And the flow in the stream consists of two components. Flow that we'll call storm flow that originates from a rapid increase in flow following the runoff from a rainstorm, and the base flow component, that is the groundwater discharge. So if this is a graph of the total flow shown here, then we might just imagine that the base flow would look like this line here, and the storm flow would be the difference between the two. So the storms will contribute this rapid rise in the flow and a fairly rapid fall. The groundwater, though, contributes really the base of the flow, and it varies through the year, but it varies slowly. And generally what we're seeing here is that it increases, reaches a peak, the base flow reaches a peak for this record in April, and then it decreases. And here in July and August, when the rainfall is relatively small, the base flow is decreasing, and this is a time when we would suspect that the recharge is in fact zero or negligible, and so this is what we would call a base flow recession. Okay, so what we're going to do is separate out the hydrograph into the storm flow component and the base flow component. And the way we'll do that is with a technique that was developed in England a number of years ago, and it works really quite well. And the idea is that we come up with a simple filtering technique that will identify some points that are base flow, and then we have to work out a way to interpolate between those points. So the idea is that a rainfall causes a pulse-like increase in the flow right here, and a single rainfall that lasts maybe a few hours, maybe a day, it will have kind of a typical duration. The flow will increase and then it'll taper off, and it will have a typical duration in many places 3 or 4 or 5 days, maybe 8 days, 10 days, something along that order. And so if we go and we take this record of stream flow, and if we break it up into segments that are that long, that are some characteristic duration long, and we pick out the lowest flow in each one of those segments, then that is a candidate for being base flow. And that's what's done here. So these points are all candidates for base flow because they're a minimum flow in the segment that I think this was an 8-day long segment. Now we're going to say that, well, if it's base flow, then base flow, because it's being discharged from groundwater, probably isn't going to vary very rapidly. And so we might be able to eliminate some of these points by applying just a simple criteria that the point has to be within 10% of the value of its neighboring points. And so we do that, and that allows us to eliminate some of these points and identify the others as base flow. And I'll show you the results of that here in just a second. But before we do that, let's go ahead and proceed, and I'll get back to this point in just a second. So here is the procedure for identifying the base flow turning point. This is developed by the Institute of Hydrology, and it's described here. It's basically what I just said, and this is written up in a handout that goes along with this video if you want to get additional details. So if we apply that filtering technique, here's the result. The orange dots are what we call the base flow points or base flow turning points. Some of the points that were in our original data set are eliminated, but many of them are included. And so we say that these points represent base flow, and here I've just drawn a straight line between these points to just kind of interpolate between them. What we see here is this interval right here where, well, basically at the beginning of the record we have relatively high flow, and then the base flow drops and it's relatively constant but relatively low here. So the interpretation is the aquifer is full right here. It drains out without really receiving much recharge, and then over this period the recharge that it's receiving is just keeping up with the discharge, and so the discharge remains about stable. And I'm plotting this. These are the log values of the discharge. I've taken the log, so this is a semi-log plot, and this is a straight line on a semi-log plot, which is indicative of a negative exponential. Okay, and we'll get back to that in just a second. So to analyze that record, and basically what I'm going to try to do is come up with a way to use these turning points and calculate what the recharge is, and perhaps get some other things. And in order to do that, I need a simple model of the aquifer. And so if this is a watershed and it's underlain by an aquifer here shown in cross-section, then we might imagine recharge comes in here and it goes to flows through the aquifer and discharges to the stream. And our simplified conceptual model is that the aquifer is behaving like a tank, shown here, and water can come into the tank as recharge. That causes the water level to rise, and water is discharging through this sand-filled hose. Just right, it's a simple analogy. So the sand-filled hose, and there's our discharge, which is the base flow. So we have we can do a simple water balance. The flow going in is the recharge times the area. The flow going out we can get from Darcy's law. We imagine, well, we know the head here and the head here. We assume that it's linear between them, and we can use Darcy's law to get the flow. And we get the change in storage because that's just going to be proportional to the rate of change of the water level. So we can do a simple balance. Here it is. We can plug in values and solve for that. And this analysis is done out in the notes. What you get is that for this simple analogy, if we have a tank and there's no flow coming into the tank, then the flow coming out of the tank will be a negative exponential. You can get this explicitly with just a simple theoretical analysis, and if we plot that up on semi-log, where the y-axis is log, then this gives us a straight line, and this is the slope. It depends on the conductivity, the area of the hose, or the area of the kind of the cross-sectional area of the aquifer, porosity, characteristic length, and the area of the tank or the area of the watershed. Okay, so if we go and we lump all these things that we can recognize as being geometric constants or properties of the aquifer, if we lump those together and just call them this term A, that we'll call the recession constant or the basin constant, then we say that this expression here is just this negative exponential. A is a coefficient that says how rapidly the flow will decrease with time. And indeed, if we plot this up on semi-log plot, we get a straight line, and A is the slope of that line. Okay, so this tells us that the flow is decreasing with time in the absence of recharge. We can do the analysis where we include recharge, and if we do that, then we get an expression that looks like this. And what this allows us to do is say that, well, if we know the flow rate at a turning point here, one of these base flow points, we can predict the flow rate at the next point there if we know the recharge, the area of the watershed, and this recession constant, and the duration of time between these points. So we would presumably know everything here except the recharge, and so this is going to be a way that we'll use to calculate the recharge between these points. And this is assuming that the recharge is staying constant. Now, another thing that we can get out of this analysis is the rate of change of storage in our tank. And it turns out that it's simply the rate of change of storage over this interval is the difference between these two flows divided by this time difference, all that divided by A. And that works out to be the rate of change of volume in the aquifer as rate of change of volume. Okay, so there are some simple relations. Here's one way that we can use this directly because we have enough information to calculate it. But if we go back into our record, here's a turning point, here's a turning point. If we take this expression and simply solve for R, then we get this. The recharge between these points is equal to these two flows, the time, and the area of the watershed, and this recession constant. Okay? So what we can do after we've separated out these base flow turning points, we can simply go and apply this equation and get the average recharge between these points for the whole duration of the record. So that's pretty good. That gives us a transient estimate of the recharge. The other thing we can do is we can interpolate the base flow from this point to that point. We just use this equation again, and instead of having T2, which is the time right here, we just make that the variable T, same with that one. And this just becomes Q between this time and this time. And so this function will allow us to interpolate and draw a line, or draw points along the line that would connect these 2 points. Okay? So that's pretty powerful. What we've done now is taken these base flow turning points, determined the recharge, determined the change in storage with time, and then also interpolated and obtained recharge on a daily basis. So here's the result. This is implemented in a program that's written to work within Excel. It's written in Visual Basic. And here's the hydrograph. The blue is the base flow, and it's separated using this technique. And even though it may be hard to tell, it's interpolated using that exponential function between these points. The pink is the recharge, and the yellow is the storm flow, shown here on this secondary scale. So you can see what it's telling us is we have recharge coming in here in these step-like pulses that correspond to these large rainfall events. So that's giving us really quite a nice high-resolution record of the recharge. This is 1 year right here. Okay, and you can see actually this point right here where the recharge is essentially 0, and that's the baseflow recession. Okay, so in order to get this to work, we need to know A, this basin constant. So if this is our record and we plot it up where this is the natural log as a function of time, then this hydrograph looks like this. Here's this part of the hydrograph where it's linear. This would be a baseflow recession right in here. These other places may be somewhat of a recession, but this one is for sure. We could fit that with a straight line, and the slope of that line, the change in log cycles over the time, will be this parameter A. So it has units of 1 over time, and in this case it would be equal to 0.012 per day. Okay, so that gives us a way to estimate what A is, and we'll have a fairly long record of the discharge in the stream, and so that'll give us a lot of places where we can fit this line to. Alright, so here's another thing that we can do. With the techniques that I've just shown, we can estimate recharge, base flow, storm flow, and the change in volume stored with time. If we add in precipitation, then we do the water balance on the whole watershed, and we get this, and we can simply solve for evapotranspiration. So that gives us an estimate of really all of these guys, precipitation and ET. Those are really the major fluxes within the watershed, and including the aquifer. So this is a very, very nice technique. It gives us resolution down to a week, or perhaps even down to the daily level. So the other thing that we can do is take these records that are on fairly short time scales and average them. And so if we have, say, a 10-year record, we'll have 10 Januaries and Februaries and so on. And so we can average out what each one of the major components of the water balance is on a monthly basis, and we can compile them, and that's what I'm showing here. Here are all the different components. Here are the months in the year, and this is the rainfall, the main component. Here's ET, kind of tracking the rainfall, and then runoff, it's holding fairly steady, and base flow, it varies a little bit through the year in this watershed, but it's tracking at a fairly large fraction of the runoff. And then in this case, this is the storm flow. We don't see a lot of changes. It's fairly uniform through the year in this particular case. We can also then blow this up and just look at the balance on the aquifer, and this gives us kind of a nice result where the recharge is shown here in dark blue, and the pink is the base flow. And so here the recharge is less than the base flow, and so in yellow we have the change in storage, and so we have a negative change in storage. So the water is flowing out of the watershed for the first 5 months or so, and then here the water is flowing in and recharging the watershed. And so we get that quantitatively on a monthly basis. Okay, so these calculations are described in a handout that's available on this with this entry, and there's also a code that is written that's implemented in Excel, and it's called CU Hydrograph. And if you open it up, there are some instructions that say how it works, so read those first. It's written in Visual Basic, so you can go into Visual Basic and see all the gory details, and you should feel free to modify it as you see fit. It's fairly easy to use, fairly easy to work with, and it's meant to be modified if you care to do that. So here's how it works. If you go to a tab that's called Data, you will paste data from a streamflow hydrograph that you're going to probably get from the USGS, and it'll be in two columns, date and discharge in cubic feet per second. You need to start here in row 4 and paste it down here. Probably best to erase the data that's already in there. So paste it there, and then if you paste the precipitation, monthly precipitation is how it's set up. Paste it here, and the units are in tenths of an inch per month. Now, there are some variations on how this is done, but in most places you can go to a site that's operated by the National Weather Service or NOAA and get the data that you need from them. In this case, don't go and mess around with these gray columns. This is taking the natural log of the discharge, and this is converting the precipitation to feet per day, which are the units that the code uses. So don't mess around with those. Now, while you're putting the data in here, you should go in and change these cells. Change these cells so that they are the Julian days of the beginning of the record and the end of the record. And if you just go and have this cell reference refer to, you probably don't need to change this one, but if you make this cell record refer to the end, the last column here, or last row in this column, then that'll be the correct time. There are parts of the program that use this in the calculations. The other thing you want to do is to go and set up these definitions: date, discharge, precip dates, and precip values. These are all variables that are defined within the Excel format. And if you go to formulas, there's a place where these are described. This is just a slide, so the program isn't active, so I can't show you how to do it. But that's what you would do. You need to make sure that those are the correct range of dates and discharges, because the Visual Basic will use these variable names to read in the data. Then you go to a tab called Hydrograph 1, and here's your basin constant A, and your segment time, and the area of the watershed. These are the only variables that you need to enter. So the area of the watershed needs to be in square feet, and so these numbers here are just where I did some calculations to convert. A lot of times you'll get the area of the watershed in square miles or square kilometers, so you just need to convert it here to the right units. And then the segment time and A, these have to be determined from the data. Probably the best way to do it is the segment time really is just going to be estimated so that you have a segment time that gives you a set of points here that looks about right. If the segment time is too short, then you'll have points that are climbing up here on these receding limbs of the hydrograph, or of the storm pulse, and you probably don't want that. And then to set up A, there are a couple of ways that you can do that. There's a page called Basin Constant, and it's set up to plot the hydrograph, or plot the hydrograph, the data here, and also to plot the log of the turning points here. Now, when you do this, when you put in your data, you'll probably have to go in and adjust the time scale on the x-axis, because the time scale is set up to show this particular data set. If you put in a different time, then it, it probably won't show any data. And if that's the case, it's probably still working. You just need to adjust the time. And you can do it by putting in the Julian days that are listed on the data sheet that we used earlier. So that's one useful application for those Julian days. So one thing you can do is just go in here and fit these straight lines, these negative slopes, and then bring these lines together and get kind of the average slope of this line. Actually, it's probably best to get not so much the average, but on the steep side of the slope. And that will be one estimate of A. Another estimate you can use is these plots here. And these, the code will go and fit groups of points, either groups of 3, 4, 5 points. And it will do a linear regression, and it will get the slope of the line that best fits those 3, 4, 5 points. And it does it for all of the points, all of these turning points. And so it calculates many slopes. And here, this shows the slopes of these lines that it shows that as a function of time. And so what we want to do is get the slope that is on the steep side of representing all of the slopes, on the steep negative slope. The idea is that if the steepest slope that is really a recession and not just some kind of anomaly, the steepest slope, that'll be representing conditions where no recharge is occurring. You could have some of these slopes like this one that is a bit flatter than this one, and even though this has kind of a linear trend to it, what could be happening here is you're getting a little bit of recharge. And so the slope isn't really as steep a drop as it would be if there was no recharge at all. So you want to get this estimate that's on the steep end. So in this case, I saw there were some outliers here, but I took an estimate that was right there, and somewhere in that range would be a good estimate for A. And here, this is also the same data that we have here, but plotted as a probability distribution. And this is a value of A, and this is the probability that A is greater than this value. So you might want to pick some fairly low probability that A is greater than this value, although not the lowest, because there are some kind of anomalous points that you probably wouldn't want to go with. So in this case, generally what I do is use these data preferentially over this one, because what will happen is if you pick A that is too small of a negative number, too close to 0, then you'll have points on the hydrograph, on the interpretation, where the recharge is negative. And recharge could be 0, but negative recharge, I don't know, that doesn't really make sense in the context that we've set the model up. So if you have a model where recharge is in there explicitly as a negative number, and that really is meaningful, then okay, you could set it up and calibrate it, and that would mean something. But right now, with our model, we're assuming that there's not really evaporation off of the water table, and so negative recharge isn't really meaningful, and so that's going to require that A is going to be on the close to the minimum negative value or the maximum absolute value that you get here. Okay, so you pick the value of A, it's 0.008, what I thought would be good in this case, and then you would press this button. This will run the code to do the baseflow separation, and you'll get the base flow turning points. And this is what we saw earlier. This is a pretty reasonable separation. It's a smooth curve here. There are not any real big jumps, and there aren't any points here that we think might be recharged but aren't being picked. So we've got really most of the ones that we've got really all of the points that look like we need to include. So this seems like a pretty reasonable segment time, and probably a reasonable value A. We'll check that a little bit more detail in just a second. So then we want to go to results by day. You go here, you press that button, then it will do all of the calculations and show you the results plotted for at least part of the data set here by day. The data showing for all of the results here on a daily basis is the data is plotted here on this page. So the average precipitation, the storm flow, the base flow, recharge, so on. They're all shown here. There will be multiple values for base flow. There are three, I guess 4 values of base flow, and these are shown. Basically, what's going on here is this is base flow, assuming that the recharge is uniformly distributed between the turning points, and that's what we assumed earlier. The base flow might just come into the watershed as a pulse, or perhaps as a sinusoid, and the model calculates all of those different possibilities, and we'll plot them here. So there are a couple of plots that are included. If you scroll down this page and check those out, those are really just meant to be examples. This is just a regular Excel worksheet, so you can go in and plot the data however you wish. So if you go then to results by month, you have you've got a long page here with all of the data that are the monthly averages, and then it goes in and averages the average. So it goes in for all the Januaries and gets the average precipitation for all the Januaries, ET, and so on. So all of the different fluxes, it averages for the month of January and really for all of the months. It gives you some summary information, how many days there are in this record, how many years it is, and then it goes and also gives you the yearly average. So if you have to just go with one number, there's your yearly average, or your it's an annual average. So I guess this is the annual average in units of feet per month, and here it's in feet per year. So this particular place, the recharge is 1.74 feet per year on average. Okay, so that's some handy information. And then there's some also some volume balance checks here. So it does the balance for the watershed, the aquifer, the vadozone, the stream, and here are the balances, and it adds them all up, and they should add up to 0. So this is a check, and they're 001, so there's a little bit of round off, but it's pretty cool. We can do balances on all 4 of the major zones in the aquifer watershed system, and they all balance. And then this place here is giving the results as fractions of precipitation. So in this case, it's 0.552 is the fraction that ET is of precipitation, and so these give also the other fractions of precipitation. And there's a plot here that shows the how the different fluxes play out through the year. So that's really the extent of it. That's how to use the code and how to get the results. Well, let's see. Here's kind of a nice plot of these annual or these monthly averages. shown here for about a year. So this the PowerPoint will be posted, so you can check that out in more detail, and along with the code itself. So go ahead and download those and see how they